Uh, yeah. Hello, everyone. Am I audible? Anyone?
You are audible, sir.
Hello, sir.
Yes, sir.
Yeah.
You are audible.
Yes. One more thing, if you want to participate in chat or Q&A, you should make a Microsoft Team account. If you will not have a Microsoft Team account, you will not be able to join the chat or Q&A. So try to have an account on the Microsoft Team. Okay. Yeah. Okay.
Okay, sir.
Sure. So in this week, we are learning the sparse autoencoder, the contractive autoencoder, the denoising autoencoder, some thing about the convolution, as well as some about the cross correlation. So in the last week, we understood about the autoencoder. So what does the autoencoder does? It basically compresses the data and uh, try to generalize the data. So it tries to convert it to certain number of uh, hidden layer, basically the latent vector, and then we decode those latent vector, and then we say that we have reconstructed the input output. So basically, when there is whatever we are giving as an input and we are predicting the same thing, we are saying that the neural network is basically trying to create an identity function. However, the identity function itself is a very trivial. Uh, when we add the parameters inside the neural network, the trivial nature of this identity function erase out, and then we compress the hidden layer, and then we say that okay, now the hidden layer and that is the latent vector is try to compress the input and try to generalize the features that is available in the input, and we are also assuming that the inputs are uh, identical nature. So they come from the similar background. They are not independent. Okay. So we are depend. They are dependent on each other. So this is our the basic assumption. Okay. So today is the 7th March. Okay. So a little bit describing the autoencoder. Then we will go to the sparse autoencoder. The idea of a sparse autoencoder. So whatever we told just now, it's like we have a function x, we have an input x, we are passing through a function, and we are creating a hidden or latent space that we are calling it j, and j is it's called f. So now this is f and this is g. So and this is x. Okay. So basically, if this f is taking the input x and this g is given, this fx is given as the input, and that is actually x. This is what we are trying to do. However, whatever we are predicting, we are calling it as a the predicted output. And this overall, we can also write this as a g of, let's call this as a w and w star, then g of w star, comma, uh, of, yeah, comma, f of x, comma, w. Okay. And these are the trainable parameters that will create the uh, this training process. This will overall, after training, this will be able to create a correct reconstruction of our input. We have also understood why we are using the autoencoder, because we want the half of our network encoded part of the network to have the compressed nature, so that we can further use it into the later part, like class for the classification or for further training or tuning. Okay, so b- we have already understood a simple autoencoder, how we train it. Uh, we train for this W and W star, and we say that once these are trained, we are able to reconstruct it. But let's say if you have a more than one hidden layer, such that you want to train it, and then you are calling that hidden layer as a deep autoencoder. In that case, you have a input layer X, and let's say you have a first encoder, and then you have a hidden layer. Let's call it this, and then you have this the decoder. Let's call it decoder. Let's call it encoder one, decoder one, and then this is the output. That is the X star. Okay. In this case, you have a W1 here, W2 here, W2 star here, and W1 star here. In this case, if you want to train for this compressed nature of H, such that currently we are assuming that H is the number of neurons in this hidden layer is actually lesser than E1, and E1 is equal to D1 in this case, let's say, in such that this is the latent space. Okay. So what you can do, you can directly train for all these W1, W2, W star, W star, W2 star, as we have learned from the back propagation. So if I know my input, if I know my output, I can directly create a loss function that will directly train it for x minus x hat. Uh, right. However, it is not guaranteed that this reconstruction will be very good. So there are different training method that you can use, and basically, let's say in this case, if you are directly training this autoencoder, your convergence is, let's say, 10 to the power minus 3 of order of minus 3. It might be another way of training in which your order can be of minus 5 or minus 4. In that case, you will have to do something else to do that, right? So what you can do in that case, uh, you will only create one layer at a time, in a way that uh, you have an input, you have one hidden layer, and then you have output. And and then you trained it. And let's say your input is way too complex, then obviously in that case, hidden layer V is trying to predict whatever input you are giving to the output. However, because the network itself is very small, it will not be able to predict. Let's say this as the input has a dimension of 784 cross 1. Your hidden layer has a dimension of, let's say, 64. output is 784 plus 1. This is good, but one hidden layer is not enough to reconstruct whatever the input you are giving. In that case, you will train it, you will get some convergence, and then what you will do, you will keep this W1 and remove this output decoder part. And then what you will do, you will give another hidden layer, you will call, let's call it H2, and you will create the another output layer that will have a same dimension as H1, and you are calling it as H1 dash. And whatever the output that you are getting here, and here let's call it W2, and let's call it a W2 dash. And then you will train for the input that you are getting on H1, and the same thing you are going to predict here at the H1 dash. In that case, basically you are trying to say that I am trying to compress whatever the input I am getting at H1 through H1 dash into the H2. Okay. And once you are training that, you will say that, okay, now I have trained my another encoder from H1 to H2, I will remove this. Okay. And then I will create a, let's say I only want a two hidden layer between input and the latent space. Then I will create a H2 dash and the output X star. Okay. Uh, yes. And then I will have a W2 dash, W1 dash, new weights, and then I will train it. So what is happening in this case? So W1 and W2 are already trained good enough such that they will converge faster and they will be able to go to a lower convergence. And in this case, this way of training will give you a better reconstruction. Okay. So either you can train directly from input to output like you do in the MLP, or you can do this step method, like step by step training the weights, removing the decoder, adding another encoder, training for those small encoding space, and then removing all the encoder and creating a overall encoder and then training for that. So in that case, what will happen? We are going to train for W1 and W2 as well after training for all the smaller. However, in that case, W1 and W2 will not change a lot because a certain level of training has already been done. Why we need the training? Because, like, let's say you are saying that, okay, I have already trained the W1 and W2, and we are only using the encoder part. We don't need decoder. So should we not do this, the another training? We need. Why? Because when we started from the one hidden layer that was acting as a latent space, the whatever the latent space learned, it was not very accurate. When we created the another layer and we were trying to learn between those H1 and H1 dash, we are not using the input X. So basically, we are trying to create a kind of we are trying to create a kind of space in which a similar kind of things are available. However, it is not matching with input because we are not in using the input at the second level of training. However, we are using the third level, that is, we are using all of them as a training. We are using the X, and in doing that, we are also retraining W1 and W2, and that is helping us to converge better and reconstruct better. However, we are always saying that in this case that H2 is lesser than H1 and it is lesser than X for the encoder part. So we are saying that we are always compressing the latent space. What if H2 is greater than H1 greater than X? Let's say means so X has a dimension of 784, H1 has 800, and H2 is, let's say, some number 850. Then what will happen? In this way, what will happen? Like we are not compressing anymore. We are saying that whatever the input I am giving, just pass it through the weights and get it to the X. Because we have more hidden layer. In that case, let's say I have a weight that has the value 1, it will simply copy that input to the H1 hidden layer. I have another weight going from H1 to H2 that is more than 784, that will simply copy the value, and then it will not be able to learn the latent space. In that case, we are simply copying those, because copying this value, and it is not useful to us. And we call this kind of autoencoder as overcomplete autoencoder. And when this kind of network you have, you call it undercomplete. Okay, are you there? Are you listening?
Yes, yes.
Yes, yes.
Sure. Okay. Yeah. Thank
So
you.
you want always under complete auto encoder. That is
Yeah,
desirable.
because we want to compress our input. We want to generalize our input. Yes. Yeah.
Mm.
Thank you. Yeah. So now let's say, even though you have made a undercomplete autoencoder, let's take a simple example of handwritten data set. Handwritten MNIST data set. And you are giving the numbers written in the pixel of 28 cross 28. And the numbers are going from 0 to 9. In this, basically, you have a 9 kind of input that you can make out of your hidden layer, and that is the latent space. Okay. However, instead of giving 10 hidden layer, you have given 12 hidden layer at the latent space. You have given 12 hidden layer. So what will the another 2 hidden layer? How can we manage that another 2 hidden layer? Can we do something so that these 2 hidden layer would not copy unnecessary data from input to output, and it would not affect our compressing the data. So what we can do while creating this loss for X and X bar, we can create a regularizer for the W that is available here between the, or you can use all the W within the network. Let's call it the theta, or you can also use the W that is available at this part between the latent space and the network before that latent space. So you can use the regularizer. Sorry. So this lambda is a regularizer constant and r theta is a regularizer. So this regularizer will help you such that whenever that theta is not needed, this will become minimum value. In that case, the another two latent space will produce the value 0, or it will, and all the w's will be minimum. In that case, it will turn to 0. Okay. So when the w's will turn to 0 in the case of regularization, then they are not producing anything, and hence we say that once we are giving the regularizer, we are not worried how much number of latent space we are providing. Okay. So that is why we need the latent space regularizer. Okay. In the latent space. Okay. Now let's talk a little bit about the sparse autoencoder. So basically the sparse autoencoder looks exactly like the autoencoder, but we have an extra regularizer, or you can say the extra loss function. So what does the extra loss function does? If instead of minimizing these weights, they minimize the activation function. So what does it mean by activation function? Like let's say you have an input X, you have a hidden layer here, and you have output. So basically, whenever I am giving one, it doesn't mean I have only one hidden, I have only one layer between input and output. It can be as many number of I want. Okay. So, and then I am saying that I have a neurons here, and these neurons, let's say neuron in L, let's say NH1, this is the first neuron. This is actually taking the input, whatever the input I have here, X11 into W11 plus something like this. Okay. X12 into W12 plus something like this. And this F is some kind of a activation function. It can be sigmoid in this case. Let's say I am saying that I want only 1 and 0 as output. In this case, if this neural network produces the value 1, we are saying that the activation is activation is activating the value. And this nonlinear function is activating the value. If this out sigmoid is producing the value 0, we are saying that this activation function is not activating the value, or you can say it is deactivating this latent space. Okay. In this case, we will say that whatever this hidden layer is trying to produce these values, if I want that some number of hidden layer producing the value should be less than 0.5 or less than 0.05 or 0.5, we will say that the sum of, let's call it A for right now, the sum of activations at H divided by number of the hidden layer is there, that should be, let's write, that should be less than or equal to 0.05 or 0, whatever the value we want. And that is called the sparsity constant. Okay. So what does it does? It is doing the similar thing. However, we are controlling the output rather than we are controlling the weights. At the end of the day, we want the output to be minimized for the over complete or the under complete when we are keeping the hidden layer more than necessary. So we don't want any output for the neurons. We doesn't need or anything. We did not know how much uh, value we want to activate at the output. So some of them will not get activated. In that case, we are giving this kind of constant. And in that case, we are using a loss that is called KL divergence. So the KL divergence is called Kullback-Leibler. Kullback-Leibler divergence. This Kullback-Leibler divergence ensures that my output is all my activations are always activated or not activated. So in that case, let's say if I have the loss that is taken as x and x hat, we are adding a sparsity constant lambda into KL loss of rho and rho hat. So what is the rho here in this case? This value that we want. That is the sparsity constant rho hat. And what is the sparsity they are producing? Like let's say, okay, this is what we want and what is they are producing. So this is the predicted sparsity, and this is what we want. And this will ensure that this is that the some of the neurons will get activated and they will not create the copying of data from one network to another. And this scale divergence is written as, just I will check the formula. So they are acting more like a what we have taken, the logistic function, the uh, just a minute. Yeah, this is written as L equal to 1 to K, 1 by K. Maybe we should remove this one. It's not needed because we are using the logarithmic function. So that is written log of rho hat plus uh, 1 minus rho of log of 1 minus rho by 1 minus rho hat. Okay. So basically, if you remember this classification task when we were using the binary classification, we were saying that if if the output is 0 or 1, if we want our output to be 1 and if it is producing the 1, then this logistic function will minimize the loss. If I want the output to be 1 but it is producing 0, then it will basically increase the value of loss and it will try to go to the infinity. However, you will always get the value between 0 and 1. So basically it is trying to maximize the value whenever you have the loss in the prediction. You have the error in the prediction. Similarly, whenever you can see that if you are saying that the rho is not, if rho is equal to rho L, in that case, this will become 0 and this will become 0 as well, because the rho by rho hat will become 1 and this will log of 1 will become 0. However, if the rho and the rho hat are not equal, in this case, this will maximize. Okay, like let's say our rho is 0.05 and the rho hat is something 0.9 or something. In this case, this value will become very large, and in that case, this will become large and this overall regularization will become larger, right? So it is acting similar, but this ratio creates, because we are having a two value and we are not comparing with anyone. In that case, we are taking this division like it's not 0, 1 or minus 1 or 1. Then this rho L is acting as a, we can say, to create this value 1 when both are becoming almost equal, and then it will become minimized. Okay, so I will show you a graph later. So basically, when we are let's say the activation outputs are between 0 to 1 and we want our activations to be 0.05, and after training the value will look something like this. Okay, for all the neurons, these are the neurons for different neurons. Okay, and then we have denoising autoencoder.
Sir, what is this x-axis and y-axis here in this graph?
So the x-axis is the what is the value these activations are producing.
Rho value.
Row value, exactly. So this is the row value, and these are the neurons.
I mean, KL value. That is it KL value?
Yes, these are the, yeah, these are the KL value, right? So KL value we will become maximum when row are basically going away from this uh, whatever the row we are giving. The KL value will try to go away. You are right.
Okay.
Okay. Now we will talk about the denoising autoencoder. So Currently, we are talking like, let's say I have an input X and we are predicting the X hat, and we are saying that after training, X hat is equal to X. Just let me check once more. Yeah, these are the KL based on the theta. Correct. Well, there is one more thing. Like once we are adding this KL, we will have a extra loss term and while calculating the gradient, extra gradient term, and that like when we are talking about this sigmoid, we were having the value something like delta into 1 minus delta, while considering this mm, the logistic regression function as a loss. Similarly, this kind of loss function will become because we have the gradient here, and you can calculate this dou k ly dou rho l, and you will get a similar kind of extra loss function. And because we are also using, because dou rho l are also dependent on dou w, so these one another term will come into the picture as well. Okay. Yeah. Now we are talking about the denoising autoencoder. So this is what we were doing earlier. We are trying to create the identical function from input and output. While we did, we are not satisfied with it because we are saying that, let's say in a space, I have some pictures. Let's say I have some pictures. I want this feature. Let's say I want this feature and this feature to find a relation with themselves. Okay. Like I want this feature to know that there is something triangular beside this. Okay. Like in a picture, you can have a multiple thing. Like you can have a dog, you can have a background, you can have pictures, you can have anything. So it should know that we are not only training for the dog and the cat. We also want to know that there is a grass behind, there is a traffic light behind. So basically, it should find a relation between their environments. Okay. So we are saying that in that case, we want the neural network to train to find their relation with their neighboring pixels. In that case, we will noise the picture in the sense that, let's say in this figure, in this image, I have some pixel, and in those pixels, whatever the original value is, such that it is showing some kind of a rectangle or this quadrilateral. And then if we will add some noise such that there will be some change in the picture.
அதுதான் கரெக்ட் தான். மார்னிங் செஷன் மட்டும் தான் செய்வோம்.
Hello, Monica, please mute. Oh, sorry. Yeah. So if we will add some noise to this picture, this will become something like this. Okay. Just a minute.
என்ன ஜெயன் சார் பாப்பாக்கு பர்த்டேவா நேத்து முந்தினால?
Yeah. So if we will add this noise here, it will look something like this. However, whatever it is trying to predict, it is trying to predict the original value. So basically, this original input that we have given for training, and this is the original output we are training for. It will say that it has to this output has to move back to the original value because we are training for this, but this is what our the input is. So this is, let's say, x tilde. This is what I am training for, and this is the output that will used for the calculation of loss. In that case, it is trying to find the relation with the neighboring pictures. In this case, let's say if I am disturbing this image, then basically it will try to find that there is some kind of joint or disjoint, whatever the available it is there in the picture, it will try to learn that. And that's why we are using the denoising autoencoder. So the process is very simple. You noise the input with some random value, like let's say this is your input. You you use some kind of a normalized random variable. You make it then you provide that into the autoencoder, and whatever the output you are getting, create the loss function for x hat and x. So you are not giving the input x anymore. You are giving the randomized input, and in that case, you will predict, and you will say that once neural network is trying to minimize this, basically it is also trying to find the relation between the pictures, the relation between the patterns that is available into the picture or the features, input features. Okay. That is the simple idea of denoising autoencoder. This denoising idea goes back uh, in the future with the name of variational autoencoder as well as the
Ini ada
diffusion
lakuin naman
models.
ngerti.
Uh, yeah. So in the diffusion models, so maybe we can talk about that later. Then there comes a contractive autoencoder. So there are different type of autoencoder that can be used for the different purpose. And in this case, we are saying that whatever we want, we are we say that if I am perturbing the input little bit, the output should not change a lot. So in this case, the gradient should be minimum. For the gradient of the output with respect to the gradient of activations with the input should not be very large, because those activations are changing the output, right? So so we are basically trying to create a regularizer for those activations. In this case, let's say I have an input here, I have a hidden layer here, and here we have the output AJ, and we are saying that since I have the input X, we will create a Jacobian matrix for all J goes from 1 to NH, and for all X 1 to M, we will create a Jacobian matrix of dou AJ by dou XM. And then we will not then we will create the Frobenius norm then that is basically summing and squaring over all the value of dou AJ, and then we will say that this gradient should be minimum as well. Let's call it R, and we will multiply with lambda, because we are always giving some regularization, because this is not what we are training for. This is what we want to minimize, because we want once we will, let's say you trained for a picture of dog, but suddenly you have given a different kind of dog as an input, then the output should not say that this is not dog, this is something else. The test error should not be large. In that case, we will use this kind of contractive autoencoder so that the small perturbation in input should not create a large difference into the output. Okay. So this is what the basic autoencoder looks like. Then the idea of convolution come into the picture. So uh, here we were discussing about like how we can train the images into the neural network, right? However, you can create a 784 input, you can create the output, but finding the features from those input itself is another challenge. And training input using a vector, be in a vector is not a very clever idea. So basically we are trying to find a method where we can train the input that has the pixel value that are in the sum of a square form or rectangular form. Can we give that as an input into the neural network directly before creating a multi-layer perceptron? And then after creating the convolution, finding the features from those images, and then we can basically flat those features in, and then we will give to the multi-layer perceptron. Then that would be a better idea than giving a, like, let's say I have an image of 28 cross 28 that has some feature, let's say some image of house, and there are some very fine details in this. But when we are trying to, our aim is to when we give a image of a as an input, our aim is to only figure out that the image has a house. Then we don't care about the what are the minute details of the roof, the minute details of the door and anything, right? In that case, we will use some kind of convolution. We will talk about that. So some kind of convolution, and we will convert this 28 by 28 dimension into some kind of, let's say 7 by 7 dimension, and then we will flatten it into 49, and then we will use some kind of autoencoder, whatever we are trying to, whatever the output we want, and then we will create the 49 output, and then again we will uh, basically build the original image. Okay, this is my X predicted, and this is my X input. In this case, we are basically we are trying to find the feature from the input. We are making the dimension smaller because everything is not necessary for us. And then we are creating the output. And in that case, we are using the convolution. So what is the convolution means? Convolution is a mathematical idea in which we say that if I have a function f, let's call it the function f, this is x. Then if I am have another function, let's say g, and this g is dependent on t, such that f of g into t is actually the convolution of 0 to t into f of t into g of t minus tau d tau. So what is happening? We have this steady function f that is dependent on t. Okay, let's write dt. Okay, and then we are moving this gt such that whatever the common area is there, that is my f of g of t. So in this case, let's say I am plotting this f of g of t. Then if this will move here, our area will be maximum, right? If we will move here, our area will be smaller. And if we will move here, the area will remain constant or something like this, right? So basically it is showing the area, and this will look something like this, right? Because the area has been maximized here. The area was minimum here, and area has become constant here. And this is sorry, this is the t. So this convolution is basically creating, just a minute. This convolution is finding the, like in this case we are assuming f and g as a continuous variable, and then this f and g such that g is moving in this direction, and the area, the common area is basically the convolution. And when we when we find the integral, basically we find the common area, right? However, let's say instead of having this continuous variable, you have a discrete variable such that you have a value at different x, right? You have another function, something like this. Then when it is there, so basically what you will do, you will try to multiply the, like these are the x1, x2, xn, and then you have a certain number of, let's say g1, g2, some to gm, right? So what you will do in this case, you will multiply g1 into x1 plus g2 into x2 such that you will go gm into xn, right? And that is what you will denote here as a one of the area, right? Similarly, if you will move here, then you will say that I will multiply g1 into xk plus g2 into xk plus 1 plus gm into xk plus m minus 1, right? I am starting from 1, so let's write like this. Okay, right? So this is what the convolution looks like when you have a continuous variable or you have a discrete variable, right? In this case, we are only saying that I am starting the convolution from where my g is. However, in many cases, you will start the convolution like, let's say this is my f and this is my base. So I will start from here, and this is the first. This is where I will get only one value, common value, and I will multiply those, and that will be my the areal value. In that case, I have no input of x in this area, and I have only input here, and so I will multiply this value, like in this case it will be gm into x1, right? Once I will move from here to here, let's say I have a 3 value now, so I will multiply g of, let's say in this case g of m minus 2 into x1 plus g of m minus 1 into x2 plus g of m into x3, right? So basically, in this case, you also have this g of m minus 2, but you have no x. So we are calling this as a, we are generalizing this formula and we are calling this as a 0, right? We are calling this is 3, 0. Then what will happen? We are saying that here, let's say this is the reference value. This is the reference value. This, in this case, we are giving this value of x as a 0. So we are creating a padding. This padding will help me to generalize a mathematical formula such that I will not have to write a if-else condition for the point where I don't have any value, right? And this padding will simply generalize this method when we are doing the convolution. Okay. So the idea of convolution is clear, everyone? Yeah. I'm not getting any response. I can explain again if you want.
Why what is the use of the convolution?
Yeah, I will come to that, but currently I am just explaining the math. Like when you have a two function, one of the function is moving over the other, what does the convolution look like?
Okay,
So,
but here you have made two groupings, no? G1,
so,
two things. Why?
so when g and is a continuous variable, this will look like an integral, right? But when you
Yes.
have a discrete value, you will do this kind of addition, right?
Mm. Okay.
But
Here two things you have put, no? G1, just slide upwards.
this one,
Just
right?
go upward. Still little here. Implies you said G1 x1 plus G2 x2 up to xm. After
Yes.
that, you started putting k, xk, xk plus 1, xk plus n. These two
Yeah. So
groupings. Means
yes,
why these
yes.
two groupings are done?
Basically, because I am moving the value of uh, I am moving this g over the time, right? So after
Right.
some time, uh, just give me this. So after some time, the function came here. This has moved to here,
Okay.
right? So I am multiplying with these x to this
Oh,
g,
okay.
right? So this is
Okay.
what. So after t equal to tau, let's say the x has moved this. It has moved to here from here to here, and then I will have a new x to be multiplied with this g. Okay. So
Okay.
we are naming this g as convolution operator. Okay.
Okay.
So, and this padding, because when I want to start from the very first value, I know that there is no value here, but since I want to create an algorithm for the coding, I don't want to write if else condition. So wherever I don't have x, but I still want to multiply, I will give them value 0, such that I will create an extra arrow into the left. And let's say I am going here as well, and my final g looks like this, then I will create the value 0, 0 here as well, such that while moving from here to here in time, I don't have to write any if else condition, even if the this g moves here, right? Because still I have to multiply one value of x with one value of g. So I am
Yes.
creating the padding that has a 0 value, and it will not contribute to the convolution. Okay.
Yes.
Yeah. Now, so convolution is clear. So according to the lecture, there was a concept of linear time variant system, and there was a concept of linear space variant system, invariant system. So what happens? Let's say, mm, let's say this G is the convolution operator, and let's say you have any speech signal. Someone is speaking, you have this kind of a speech signal. And in this case, this speech signal is a discrete value. So here's this kind of value you have at different times. Okay, right? At different T1, T2, T naught, T1, T2, right? And then I want to, I have a convolution operator that is also discrete, and that has a value of H naught, H1, H, let's call it G1 to not confuse, G1, G naught, G1, G2, G3, and G4. I have a, let's call it up to GM. I have G0 to GM as a convolution operator, and this T node at these are the value of my F T0 to, let's say, Tn, such that generally Tn is much larger than M. Okay. In this case, I have a value of G1, G2, G3, G4, G4, Gm up to Gm. It might be any value, but let's say if I have a delta function del t that is of one of the Gi, and that might look like 1 when t is equal to n else 0. Okay, so this is also called Kronecker delta function. Yeah, this is the Kronecker delta function. Generally, this is delta function, but when we say Kronecker delta function, we say that if I is equal to j, the value is 1. If I is not equal to j, this is equal to 0. However, remove the Kronecker and they say that at any n, the value is 1. Otherwise, it's 0 when n is equal to m. Or let's write n is equal to m. This is just a kind of operator, the convolution operator. It can have, we can have a many kind of convolution operator, but let's say I have a one kind of convolution operator, and when I am multiplying this T0, T1, T2, T3 to Tm, in this case all these values are 1. In this case we will sum the value of G1 plus G2 plus G3. Sorry, we will sum the value of this F1 plus F2 plus F3, because for that value these are given as a 1. So whatever we will multiply with F, this will give as a 1. Okay. Similarly, if you want to have a space independent variable, let's say if you have a pixel values of 100 by 100, let's call it like n cross n. Let's call it if you have an image of n cross m, and then you are creating a convolution operator that has a dimension of, let's write f of dimension of uh, x cross, let's write j cross k, such that j is much smaller than n and k is much smaller than m, smaller than m, and it has some value 1, 2, 3, 0, 4, 6, 5, minus 1, 3, 6, something like this. It can have any value, and it has some value 1, 2, 3, 4, 6, minus 1, minus 3, minus 1, 0, 1, 5, minus 3, 4, something like this. Let's write some value here as well. Let's write 2, and then all the values are filled here. And if we will multiply the value of f into g, and we will create the convolution for the all the space, in this case x and y, let's call it x and y, then what will happen? Basically, you will if your convolution is here, if your convolution operator is here, then it will multiply with their respective uh, units. Like 1 will multiply with 1, plus 1 into multiply with 2, then 2 with plus 2 with multiply with 3. Similarly, and you will get a value. You will get a value. Okay. Again, you have get a value here. Then you will move your convolution operator to the right hand side. You will do the element wise multiplication and addition. You will get the another value. Similarly, you will move 1 here. Am I correct? Oh, sorry. You will move 1 here. You will create the another value. If you will move one more time here, you will get the another value. Right? Similarly, if you move downside, you will get the another value here. Right? Because you are doing the element wise multiplication and addition. And similarly, you will get some value. What will be the dimension of this matrix? In this case, it will be the dimension of n minus j plus 1, comma, cross m minus k plus 1, right? Let's say this has a dimension of 6 by 6, and this is a dimension of 3 by 3. You will get a 4 cross 4 dimension, right? Correct? However, we were not considering the any padding. And let's forget about the padding for now. So what is this G is doing? So basically, I will have to, let's say I have a picture of a house, a very nice house, a good old Indian architecture or a old European architecture that has a very intricate designs. And then what you are doing, you are creating a kernel or the convolution operator that is creating some kind of value of dou y, and dou fy, dou x, such that it might look like, let's say if this is the y direction and this is the x direction, then what it will do, it will create the something 1 2 1 0 0 0 minus 1 minus 2 minus 1 kind of a kernel. And if we will pass it through the this image, it will create the value of gradient. And when you are trying to create the value of the gradient will be maximum where there is a large change into the value of the pixel. And where is a large change in the value of the pixel? When there is a, let's say there is a pillar, so there is a white light here, and there is a sky here, then there is no light. In that case, there is a gradient here, right? There is a gradient here. Here there is a gradient, right? So it will create a line here because of this G, and that G will tell about the features, or you can see the edges of those picture of that architecture. Similarly, you can calculate the df by dx using another kernel, and you are calling it as a 1 2 1 0 0 0 1 minus 2 minus 1. In this case, you are basically using some kind of a second order differentiation. Okay, and you will get this kind of feature if there is a available. And if we will add both those features, basically you will get, this is giving you the vertical feature, this is giving you the horizontal feature available in the architecture. And if you will add those features you have got after the convolution, you will get a nice picture that will show only about the edges of that picture, right? So these G's are basically acting as a network, acting as a differential operator, right, over a image that has a discrete values, and this G also has a discrete values. If you might have any continuous values over this xy, you can also create a continuous dou f x, dou f by dou y, and dou f by dou x, and you will get the similar kind of uh, you can say the similar kind of feature, but that will be continuous. So that's how the convolution is helpful in finding the features into your whatever the input you have into the in your input. Okay. In neural network, in the convolution neural network, what happens? These values basically are the trainable values. So we don't know what are the values that will create a nice feature. In that case, what we do, we initialize some value of W1, W2, W3 here, and we say that once the neural network will be training, they will be creating feature by training these Ws. Okay. Other than these multi-layer perceptron as well. Like since we are creating this feature from 28 to 7 by 7, just like we did using this kernel, like it was reducing the dimension of the image. If we will use the padding, it will not reduce the dimension. Let's say in this case, I have this picture, okay, and if I will add two another features here and two here, then it will become two here as well and two here as well. So it will become 10 cross 10, right? And if I am using this 3 cross 3, then what will happen? Uh, am I doing some mistake? Am I using extra padding? Maybe I will have to add one padding, and in this case, I will make a 8 by 8 picture out of 6 by 6 by adding one padding both sides. And when we will use the convolution, again it will convert into 6 by 6. However, sometimes you don't need the padding because you really want to reduce the size of the image. And there is another concept other than padding, that is taking the mean of uh, these images. So what does that mean? Like, let's say in this four, uh, let's say in this picture, you have the pixels here available everywhere. And then what you are doing, you are saying that either I will create another pixel G that is non-trainable, but what it will do, it will find the maximum value of these four value, and then it will create another image that will only take the maximum value. In that case, out of these four, you kept the maximum value here. Out of these four, you kept the maximum value here. Out of these four, you kept the maximum values here. Out of these four, you kept the maximum value. And what will happen? It will suddenly reduce the size of your image. Either you take the mean value or you can take the maximum value, because you don't really care about the very intricate features that is really a small and that is not necessary for classification. Okay, so that kind of taking the mean or this min max value or the mean values are taken after finding these features, and these are repeated. So basically a simple convolution will look like you have a picture of, let's say, 28 cross 28, then it will get converted. Let's say I am using the padding, so I have a 28 cross 28, but it has been passed through a G. Then I have used the min maximum value of, let's say, 2 cross 2, then it will become 14 cross 14. Then again I have passed it through some kind of G, then again it will with padding. Let's write with padding, and again I will pass through some kind of mean value or the max value, and again it will become 7 cross 7. So basically this we use this kind of convolution layers.
How is this 28 by 28 becoming 14 by 14?
So what I am doing, I have these input features here, and I am saying that out of 4, I will only take a value, and that value can be either mean value of all the 4 values here, or I will take one of the maximum value of them. There are different ways of doing it. Let's say I am doing a mean value of these 4 values, so this will become one value, right? Similarly, I will take the mean of those, then it will become another value.
So that means out of 28, you are taking only 14 values.
Yes, I'm saying that everything is not important for me.
Yeah, selectively. So this from first transformation, 28 by 28 to 28 by 28. How you get that one?
So I have a convolution operator. I am saying that convolution operator has some value of, let's say, 3 by 3, and I am adding a padding at all the 4 sides.
Okay. The
And then
remaining
I'm
things you are
saying,
adding.
yes. And then we are saying that, so let's do not disturb the algorithm by using if and else. So I am just adding a padding. And after padding, I am doing this convolution. And whatever the output I have got, I am assuming that this G is trainable. And once we are training this network, this G will be able to find the best kind of the value such that it will be able to extract the feature out of this image into the best way. Okay. And you can call the combination of these two as a one convolution layer. Finding one convolution layer with one min-max layer or a min layer. This is the another convolution.
So padding is with what values you will be padding? 0, 0.
Yes, 0, 0s.
Okay. Thank you.
Yes. So this is the one convolution layer and this is the another convolution layer. And this convolution layer is basically making the input size smaller. And now I have a 7x7 output here after two convolution layer. So then what I will do, I will basically flatten it. And then it will become 49 cross 1 as an input. And then I will pass this through a autoencoder layer. I will get the output. Then I will basically then again I will convert this 49 cross 1 into 7 cross 7. And then again I will reverse whatever I have given. So I will make a reverse autoencoder here. And then I will train it. Okay. So what is happening now? Now, whatever available it is into the input X here, everything is not important. That is the first thing. And not everything is participating into the loss, right? So isn't it wise to not include everything, because not everything is important. Let's say if you have a lot of features here and you have to only see that, okay, I only care about is it predicting house or not, then why the small feature is participating into the loss, right? It has to only figure out that edges might look like house, right? Something like this. And if it is able to figure out it looks something like this, then okay, I am fine with it. So this is what. And if you will write the code of a simple MLP, a kind of autoencoder in which there is no convolution layer, it is much harder to train for the images. However, if you will use the convolution layer, do some convolution, then create this MLP in between and again deconvolute it, then your convergence will be much faster. Your test loss and train loss will be much better compared to what you were doing earlier. Okay. Again, like we have understood the denoising autoencoder. So we can also make the noise into this image, and then we do this kind of convolution operation, then min max operation, then convolution min max, and then create this image, then create this output. So we can also do that, and that's how we will know that which one is acting better and which one is better for what purpose we are making our algorithm, we are creating our model, and we want to use it for the other purpose. Okay. So this is what the overall idea of this lecture is. There is another concept of cross correlation. So what does it mean by cross correlation? Basically, the name itself says that if I have an input A and if I have an input B, if I will take the dot product of A and B, if it is 1, then A and B are similar. If it is 0, then A and B are not similar, right? So this dot product itself is telling about the correlation between these two vectors, right? These two vectors. So, or also, if you can also think in the way of loss, like your input is A, your output is B, and if you're trying to find the difference, and you are summing it, like let's say this is the loss. So let's say AI and BI for one all the n, and you are saying that if this loss is smaller, then they are correlated. If the loss is higher, then they are not correlated because they are not same, right? In this case, if you will expand it, it will look like sum of AI square plus sum of BI square minus 2 of sum of AI and BI, right? And any number is highly correlated with itself, assuming A and B are normalized value. So this will always give a 1. This will always give 1, right? So what will happen if I am saying that our loss is small, then A and B are the correlated, that means this should be large, right? That means this should be 1, right? And that is what we were.
Why this first one, sigma A square becomes 1?
Because you are, let's say AI is a unit vector. And
Okay,
if
for
you,
unit vector, okay.
yeah, I mean, assume that everything is normalized and then we are working on that.
Okay, okay. Thank you.
Yeah. Or if you don't want it to be normalized, then sum it by sigma I square. Then again, it will become 1, right? So you can do the normalization later or even earlier. So either way, it is fine. But let's say you have a normalized vector. You will say that if the dot product is 1, then they are similar. If the dot product is not same, then they are not similar. So basically, if you will try to write into it like A1, B1 plus A2, B2.
So for unit vectors, this applies.
Yes.
Unit
If this is
vectors.
not the unit vector, you need to normalize it.
Yes. Okay. Okay. Okay.
It's not that this is only valid for unit vector. If it is not, then normalize it. Okay.
Okay.
Just for having a confidence in the mathematics. That's all. Yeah. So basically, you can write this as a something like what we were learning into the convolution. So I will ask a question. Is this cross correlation and this convolution is the same or is it different?
Different.
How? Can you answer?
Cross
Yeah.
correlation is one function is constant, no? That matrix 1 1 0 0 0 0 minus 1 minus 2 minus 1, that is a constant. Same thing is applied here. There is no such a restriction or requirement.
Let's say I have trained a network. My G operator is fixed now. Now they are same or different?
For a train vector, train the model, it will be same, constant.
No. So yeah, so the way you answered, I had to ask this question. So basically, that is creating a feature. So see, uh, you have to understand that what the convolution is doing and what this correlation is doing. It is telling you about the similarity index. The convolution is trying to find out the features. So they are not at all same. It's just two different mathematics that look same. But if you will go deeper into the mathematics, they will not look same either. Right? So that's why I just wanted you to explain that accurately. That's why I cross questioned. Okay. So this is overall in this lecture in this week. So let's see some questions and then we will finish this lecture. Okay.
I have one question for that matrix.
Finally, your own question, sir.
Yes. Yes.
Convolution, you explained. Correlation, cross correlation, you explained.
Mhm.
So cross correlation is more about similarity and dissimilarity of two vectors. How you
Mhm.
measure the thing. Convolution, you are saying that is about Two functions and
It's about finding the features.
About
Finding the features, or you can say like, let's say you have a A1, you have a n element. In the B1, you have the n element, right? Then you multiplied each element with each other. However,
yes.
into the convolution, your A has the n element, but B has the m element, right? So
Yes.
both are not same. You are just plucking the some part of A and they're multiplying with the B, and they are saying that, okay, if I am getting some value, that is about finding the features. It's not like we are trying to say that they are similar or something like that, right?
Yes.
Yeah.
Yeah.
And
What exactly when you are multiplying with that window, whatever
yeah.
matrix, 2 by 2 matrix or 3 by 3 matrix, you are multiplying it and moving it across. Exactly
Yes.
what is it that you are doing by changing different set of numbers, you will get same thing. So what is it that is getting done there?
Yeah. So I talked about that. This
Yeah, you
one.
get the numbers, so it's okay. But what is the
Yes.
significance of those new matrix to the old matrix?
Yes. Yes. So I think you missed it. So let's say you have an image of architecture. Okay. And this architecture has a very intricate design, a lot of features. Okay. Like a lot of pixels having a lot of small values.
Okay.
However, let's say this, just a minute. This G, if I will roll on to that image and the convolute it, basically it is giving me the gradient in the y direction. Okay.
Oh,
So when you try
yeah.
to find the gradient, basically it is telling you the features that are sharp in the y direction. Okay. So if you know about the Sliren, do you know about the Sliren?
Yeah,
Okay.
gradients, yes.
Yes. So basically it's like a Sliren, right? However, I have given you a perfect kind of a G that is acting to find this gradient, right? But in many inputs, we don't know what we need. We only want to give some input, do some classification. So we are initializing these 1, 2, 3 as some, I mean, whatever the value 1, 2, but we are saying that this is not the fixed value. And neural network will train these values such that this will learn itself to find the feature.
And how do you decide this G matrix which you are moving? From
Yes.
where you get this G?
Yes, yes. I talked about the G only, that G has some elements, right? Like in this case, 1, 0,
Yeah,
minus 1, 2,
those
0.
elements, how do you get? That is what.
Yeah. So when you create the network, you initialize the random value into this matrix. Okay. Okay.
Okay.
And when you do uh, this the operations, you will not predict whatever you have given at the input, because these G were the random. These MLPs were the random, right? This W that you initialize, that were random. However, we are saying that these W should be trained. These W that inside the G can be trained. And if we are training that, then G will shift itself such that from here to here, after training, you will see a nice feature. This G is able to predict it. Okay. So this is the part of training. This is not we know from early. We are just doing some operation to make the input smaller compared to what we had earlier.
Yes. Okay.
Okay. Yes. Another question, Santosh.
Yeah. So like weight, this matrix is determined in this process, training process.
Yes.
Right.
Yes.
Right. But that matrix, suppose in one case you have shown it is a vertical edge, in another case it is a horizontal edge. But suppose if something is slant, or suppose some matrix, some training is done and the matrix has been calculated to detect vertical edges. But then in another image in which horizontal lines are there, this will not be of use, no?
No, but that is what the training means. Like whatever the available into the features, they will create the G such that they will try to predict the horizontal as well. You understand what I mean? Like, you are not fixing the value of G. They are getting trained. And like, let's say if you are using the MATLAB, have you ever used the MATLAB?
Basically, basics.
Yeah. So MATLAB has filters. Okay. And they are the inbuilt filter, like this G acting as a filter. And if you apply those filters onto some image, they will give you the vertical lines and horizontal lines. Okay. So those filters are already tweaked in a way that they are built for some purpose. Okay. So, okay. However, in neural network, we say that we don't know how this filter will extract the feature, but we will randomly initialize some value, and while training, it will find. And if your loss is going below 10 to the power minus 3, minus 4, you will be assuming that the filters are doing their work, right? Or basically, let's say uh, you have trained the network. After training, basically you can visualize your, uh, after saving all those weights, you can take these weights, apply onto your original image and see what this filter was actually doing after the training. Understood?
Okay.
So this is what the example I gave. It's for the understanding. This is not the exactly two things they are doing. They can learn the slant, they can learn some kind of circular thing, they can learn something curved thing, whatever they want. So basically they will tweak the values between the G such that they can efficiently find the feature in a smaller number of convolution layer, right? Like in some, like let's say you are taking the image of somewhere in Russia, and those Russian houses has a very sharp features. But let's say if you are taking some image from some other country, let's say France or something else, they have these curvy features. And if you are training for all the data from the images of Russia of the home, they will not be able to do good on the France image, right? Because they have a different kind of house. So you will have to train for both of them differently, or you have to use different kind of image.
Okay.
Got it? Yes.
Got it. Okay. So,
Yeah.
so just to confirm our understanding, suppose one data set is having images which are having a lot of vertical edges or vertical lines or vertical buildings, columns, etc., and very few or none horizontal lines. And when that training is done, that matrix will be very similar to what you have shown earlier.
Yes, yes, because it is not going to
Okay.
learn the horizontal.
Horizontal.
That
Okay.
yeah,
Okay.
yes.
Okay.
Yeah. Like let's say you are using only one convolution layer. Okay. So basically, whenever you are thinking something, try the simplest network and train it, write the code, and your concept, what you are thinking, you will be able to basically reconfirm that you are thinking in the right direction. And that will actually help to increase your confidence, right? Yeah.
So training means you're finding weights. That's all, right? Weights
Yes,
and
yes. Finding weights and then plotting it and checking onto the original image. Like, okay, let's say, like you trained it, you got the input, you got the output, you got the classification, everything is fine. But you have to, if you can plot the weight, if you can find some meaning within the weights, that's the best thing everyone wants within the world. The more you understand about the hidden layers, the more you can create list memory based models.
okay.
Okay. Yeah.
How many hidden layers optimum one? How you will arrive at the number of
So
optimum required?
depends upon what kind of data you are using. Depends upon what's your purpose of the training. Are you reconstructing it? Are you classification it? How much diverse its data is? Is it a denoising autoencoder? So there are a lot of free variables that you have to play with. You cannot answer this kind of question directly. Okay. So it's
Okay.
all comes with the experience. Okay.
Empirical. I mean, you do it and see.
Yeah, do it and see. There is no theory for that.
Which matches best.
Yes.
Okay.
Yeah, like you once you will start doing it, you will know. And similarly, papers are there to generalize things like they like let's say you are doing the MNist, someone has already done the MNist. You just go and read that paper and you will know this is the best I can do for that. Yeah, so that's why the data is there. Yeah. And if like you already have some information, tweak the information and see consequence. That is the best.
Great.
Yeah.
Okay.
Yeah.
But
Just
finally,
a minute.
everything is based on some computations, right? A
Yes.
set of computations finally.
Yes, yes. Just a minute. Yeah.
Type of projects need more hidden layers, which will require less or some sort of thing.
So, see, I mean, you can create your data first thing.
Okay.
Like let's say you use some mathematical function, use one random parameter and create 3-4 examples of that. Like let's say you write y equal to x square plus bx plus c, where a, b, c are the three variables, right? However, this is a quadratic equation. And change the value of a, b, and c, and maybe you can create 9-10 examples of different ABC, and then try to train it, right? So you can create the data, like to play for the smaller network and everything, right?
Okay.
Yes.
Thank
you. Yeah. So this is the question. Are you able to see it, right? So this is the question we should we have to answer.
See. Yes.
Yeah. So let's solve the first question. Select the correct options about the sparse autoencoder. The statement 1 is a sparse autoencoder introduces information bottleneck by reducing the number of nodes at the hidden layer. Is it correct or incorrect? The idea is to encourage network to learn an encoding decoding which only relies on activating a small number of neurons. So we are not reducing the nodes, right? We are saying that we are only activating a small number of neurons by giving a row that is of a smaller number, right? So statement 1 is false and statement 2 is true. So option C should be the correct, right? I have also shared a link into that. You can go and click and you should go and read that. Okay. Okay. The option to question 2 is select the correct option about the denoising autoencoder. The loss is between the original input and the reconstruction from a noisy version of input. Correct? Right? The option B is denoising autoencoder can be used as a tool for feature extraction. True. So the both of them are true. In the denoising, we are first creating the noisy version, and that is the input. And then whatever the output we are reconstructing, we are creating the loss from the original input. So that is the option A is correct, right? Okay, sorry. Yeah. So let's see this question, question 3. Which of the following autoencoder methods are corrupted version of the input? Which of the following autoencoder method uses the corrupted version of input? So we have just seen the denoising design, right? So option D should be the correct. Yeah, very simple questions, nothing to.
Which one is correct?
The denoising, like we are using, we are at. Yes, go on.
Okay. Denoising.
Right. Yes. The question 4 is, which of the following autoencoder method uses a hidden layer with fewer units than an input layer? Overcomplete, undercomplete, sparse, or denoise?
Under complete.
Right. Option B should be the correct one. Yes.
Under complete is correct.
Yes. The question 5 is, which of the following is false about autoencoder? Autoencoder possesses generalization capabilities. Correct. Autoencoder are best suited for image captioning task. Not correct. Right. It can be used for anything, not only image or any data. Its objective is to minimize the reconstruction loss so that the output is similar to input. Correct. It compresses the input into a latent space representation and then reconstruct the output from it. That is also correct. So option B should be the incorrect.
Yes.
So option B, correct. Find the value of d into t minus 34 into x of t minus 36, where dt is a delta function and star being the convolution operation. So basically, d is saying that wherever the t minus 34 and t plus 56 are equal, the value will be x something. So basically,
so your Kronecker delta function is 1 when it is so
yeah, I mean, when the input is similar to, or you can say the shift is similar. I mean, whenever the shift is same, then we can say that it will produce the value 1. However, yeah, this should be
correct.
t plus 34 actually. Okay.
T plus 22.
Yeah, so option C should be the
56
correct
minus
answer.
34, 22.
Yes. The option 7 of the question 7, the impulse response is the output of dash system due to the impulse input applied at t equal to 0. So whatever these things, whatever we have studied, they are always applies for the linear time invariant and linear space variant. Okay. So we have already seen that. Okay, so I did not talk about the linearity, but we already know about from the mathematics that if x1 tends to, if I am giving input x1 and the output is y1, if my input is x2 and output is y2, and if my input is alpha x1 plus alpha x2, my output should be alpha y1 plus alpha y2. And if that is correct, then the linearity is satisfied, right? Correct? So the option should be the linear and time invariant. If we are talking about the invariance and in the time, then
Please
the
come
solution.
again. Yeah, impulse response is the output of linear and time invariant. That is what you are saying.
Yes. We were doing this G into F, right? Or G. So G is basically the T here. The H value, the impulse value. G is the impulse value. And whatever the input is, that is, we are multiplying it. And once we are doing that, we are basically doing element-wise multiplication kind of thing. And that is exactly what the linear system looks like, right?
Okay. So how it is time invariant?
So when we were shifting the value, so the value of G were always constant, right? The G were not changing. The only the X were changing. So the impulse response is invariant, right? It is not changing.
Yes. Response is invariant.
Yes.
Okay. Great.
The convolution of input with the system impulse function gives an output of a the convolution of input with system impulse function if an output of linear time invariant system. The same question.
Same stated
yeah.
differently.
Yeah. Yeah. So this is the figure. Given the image below, the row 1 is the original image, row is the noisy input, and row 3 is the reconstructed output. Given, choose one of the following variants of encoder that is suited to get the row 3. So that's basically that is the denoising, right? This is your the top one is the original input that is used for reconstructing the loss. The middle row is basically the original input. I mean the noisy input that we are giving to the autoencoder. And this is what after training we are predicting, that is the row 3. So this is the denoising autoencoder. Yeah, I was waiting for your answer, but it's fine. Option C is the correct, right? What is the which of the following is true for the contractive autoencoder? So penalizing instances when a small change in input leads to the large changing of encoding space. True, right? When we are changing the perturbing the input, there should not be a large change into the encoding space, right? There should not be a large change into the output. So yeah, option A is correct. Let's say penalizing instances when a large change in input leads to a small change in. This is not the concept at all. The penalizing instances where a small change in input leads to a small change in. Okay, so we are not penalizing the option, right? When there is a small change, then we are not penalizing it. When we are only penalizing when there is a small change in input leads to a large change in the encoding space. So option A is correct, right? Yeah.
Okay.
So these are the very simple concept. However, I will share some code. I have already written it using DeepSeek. So basically, if you are not very good in programming, you should you try to use the chat GPTs and try to generate the code in which language you are comfortable. I will give you a PyTorch code. The time is not allowed, so it will take a lot of time to explain. But maybe in the next class, I will explain that. So yeah, I will, but I will share a folder with a link, and you can run that code into your computer. Basically, I am able to run into my MacBook, M2 MacBook, so maybe you can also run into a computer with at least octa-core CPU design as well, because they are not very loaded. Okay. And I will try to 3 code and you can run it. Okay. So I think I will stop recording. Yeah, and if you want to use